All right, welcome back, everyone. So today we're going to be covering a completely different topic. We're going to start with combinatorics. Today we're going to look at geometry, but more specifically, circle geometry. And circles are very unique shapes. I love solving circle geometry problems and dealing with those shapes. They're really fun 2D shapes to work with. And so let's get to the topic. But first, what is geometry in general? Geometry is basically the mathematics of shapes, sizes, lines, positions, and dimensions. You can have 2D shapes, which is flat geometry, and you can also have shapes in 3D, which is solid geometry. You can also have 4D, 5D, 6D, but that just gets very complex. Basically, geometry is a Greek word, actually. It means to measure the land. So the first part of geometry, geo, it represents land. And then the last part of it, metry, it sounds like measurement, which it does represent. It represents measurement. We have some more people joining. Okay, sounds good. So that's basically what geometry is in a gist. But we're gonna, as mentioned before, we're gonna focus on circles. So there are a few properties of circles you need to know before we move on to the next few concepts. So what is a circle in general? It's a geometric shape where each point on its perimeter, we call that the circumference, is equidistant to a point called center. Basically what equidistant means is that each of those points on the circle, so a circle has infinitely many points, right? Each of those points on the circle are the same distance apart to the center of the circle. So that's what makes a circle. And the distance from any point on the circumference to the center, so that distance is called the radius. And if you double the radius, it still passes through the center, but then it also meets another point on the circumference. So one point on one end of the circumference to another point on the other end. And that's called the diameter. And if you guys have trouble visualizing like these terms, like what they mean, I have a diagram on the bottom right of the slide. So right here of the circle, and with all of its different properties. And you see the terms are here as well. So just to help you like visualize what these terms mean, right? We have a few more terms to cover. A chord is a line where who has endpoints on 2 points of the circumference. So like 1 point and the other point, that makes a chord. But that it doesn't have to necessarily pass through the center point. So it's not always going to be a diameter. A chord is just a line inside the circle. That's not the diameter, but still passes through 2 points on the circumference. And on the other hand, we have a tangent. A tangent is different from a chord and diameter. It only passes through 1 point on the circumference, but it lies outside of the circle, not inside. And a cool property about the tangent is that it is always perpendicular to the radius. So I can show you what that looks like. I'll just bring up my whiteboard. So I mean by the tangent being perpendicular to the radius. So I'll have to draw a circle to show you that. Right here we have a circle. And let's make a tangent line. This looks like that. Don't care about its orientation, right? We have more people joining. And let's say it, let's draw a radius. So it has to cross center and then touch that. And so what I mean by perpendicular is that it's right angle at this point. So that's what I mean by perpendicular, right? So you have a tangent line and you have a specific radius. It has to be one specific radius. If it has like a different slope, that means it's not perpendicular. This radius has to be also touching the point where the tangent line touches the circle. And that's where the two lines are perpendicular. Are there any questions? Or is that good? Hopefully that's clear. Okay. Let's go back to the slideshow. Right. So those are the important properties of the circle I need to know. You can notice on the diagram below that there's some other terms like sector or segment. Just ignore them for now. So just remember radius, circumference, diameter, chord, and tangent. So those 5 terms. They're important to know. Okay, let's continue. So we have to cover those before we go on to this part, which are circle theorems. You probably have heard some of them, but we will go through them together. And not only will we just look at them, we will also try to prove them so you can see how they are developed, how they were invented, basically. So let's get started. First theorem, we have the Star Trek theorem. It's called that because this quadrilateral right here looks like a Star Trek. But anyways, the property is that the angle on the top, so in the Star Trek shape, the top angle right here, let's call it A. This angle right here will always be half of the angle of this bottom angle right here. That is outside of the Star Trek, which we can call 2A. So let's prove that. Okay, let's clear some of these. Now we can keep that. Hopefully this doesn't take too long. Drawing is a little bit finicky on this, especially doing geometry. It's a bit finicky with this whiteboard, but I'll try my best. All right, so we want to prove that this top angle of the Star Trek is equal to half of this bottom angle that is outside the Star Trek, but it's on the bottom corner, right? So the way we prove that, we want to draw some helpful lines. When you're trying to solve geometry problems, it's always useful to draw some extra lines inside the shape, so you can help solve like those mini problems first until you solve the big problem. So the helpful line that we're going to draw is from this point to this point. Oh yeah, also I forgot to mention this, but this point right here has to be the center point of the circle. So this point where you have these 2 segments crossing and this segment crossing, this has to be the center point. Otherwise, this theorem doesn't work. Okay, so why did I draw this helpful line right here? Well, you can see that we actually have formed 2 triangles right here. And the good thing about these triangles is that they're isosceles triangles. That means 2 of their sides are equal in length. And why is that? So let's call the radius R. So remember that this point is the center point, and then so 3 of these lines meet the center point. Each of these 3 lines are actually the radius because they go from the center point all the way to 1 point on the circumference. So each of these have, say, length R. So each of these 3 lines that touch the center point right here, they all have length R, or they are the radius of the circle. Okay, never mind. And let's give some names to some of these angles. Let's call one of them A. And let's call another one B. B, got it. Okay, good. So I'm going to call this angle right here. So between this radius and this large line right here, this line segment right here, I'm going to call that angle A. I'm going to call this angle right here B. So between this radius and then the right side of the Star Trek, that's B. And they're not necessarily equal to each other. But what we notice is that since this triangle, so both these triangles actually, but let's look at this triangle. Since this triangle right here is isosceles, so it means two of the side lengths are equal. That also means that two of its angles are equal to each other. And what that means is that we have another angle that's also equal to A. And that's this bottom line right here. So between this line and then that radius, that is also equal to A. Hopefully everyone understands why. And similarly, on the right side of triangle, we can have angle B as well. Oops. So angle B between this right side of the Star Trek and then the radius, that is B. And now that we have those two angles, we can also express the third angle in each of these triangles, right? Because angles in a triangle have to add up to 180. So that means if we take 180, so let's look at the left triangle. If we take 180, subtract both of those A's, we get 180 minus 2A as our third angle. I'll put it right here, even though it's a bit too big, but hopefully you guys understand. It's the angle between here and here, those two radii. And similarly on the right side, that's 180 minus 2B. I'll just leave it like there. Hopefully you guys know where these angles are. All right, now that we have these angles right here. So these two obtuse angles. Obtuse is where, well, it's not necessarily obtuse, but in this case, obtuse basically means where the angle is larger than 90 and also smaller than 180. So we have these two angles, but we all want to find the angle in between these two radii, right? So what we can do is that since we know that full rotation is 360 degrees, right? We can add up these two angles. So 180 minus 2A and 180 minus 2B. We can add them up. Let's see what we get. That's equal to 360 minus 2A minus 2B. All right. Let's make another text box. Okay, so remember that we want to make these three angles right here. So the angle between each of these radii. So that radii is just a plural form of radius. So we want to make these three angles add up to 360. So how we can find this bottom angle right here is we just subtract 360 from this term right here. So let's do that. So 360 minus, in brackets, 360 minus 2A minus 2B. If we expand that, what do we get? Can someone tell me what we get from here? Here, I'll do it myself. So if we expand that, we get rid of these 360s. Oh, looks like someone has an answer. Yeah, 2A plus 2B, perfect. Right, so we got rid of those 360s, right? But then remember we had minus 2A and minus 2B. But then since there was a negative on the outside, these become positive. So now this just becomes 2A plus 2B. So 2A plus 2B is equal to this angle right here. Here it's a bit distracting, put it on the outside. So 2A plus 2B is equal to the angle between these two lower radii. And how we get the Star Trek theorem proof is, look over here. So look at the top angle, that's equal to A plus B. Right, you just add those angles together. If we notice, A plus B is just half of 2A plus 2B. So that means this top angle is half of what this bottom angle right here is. So, and then that's our proof. Are there any questions? Give me a thumbs up if you understand the Star Trek theorem. Oh, we see a lot of thumbs up. Nice. All right, good job, guys. Well, let's go back. There's a few more to do, a few more proofs. Next one is easier to prove. We have the right angle theorem. So basically, when you have a semicircle, so DB, so this line segment DB, that's equal to the diameter of the circle, and A is the center point. So we have this angle right here. It's still considered an angle, even though it's a line. It's 180 degrees, anyways. So we call it DAB. If we name the angle, it's called DAB, and that angle is 180 degrees. And the proof, but the theorem states that if you have the semicircle and you draw a triangle from the diameter, that means that DCB, so like the top angle right here, has to be a right angle. And the way you prove that is very simple. We basically use the Star Trek theorem to prove this. So remember, the Star Trek theorem is that you have to have 4 line segments. So one from D, part of the circumference, to C, and one from D to B. And then you have 2 line segments that connect C and B to the center of the circle, which is A. Similarly, this is also the same. Okay, so you have C to D, C to B. Pretend that A is a point as well. But A is actually the center point. So we have to connect D to A and then A to B. And we can use the Star Trek theorem here. So that means this top angle has to be a half of this angle that's between D, A, and B. So 90 degrees is a half of 180 degrees. So that works. Give me a thumbs up if you understand. Okay, that's nice. Let's continue. Inscribed angle theorem. So what this means is okay, more thumbs up. So we have this, now we have an inscribed angle theorem. Inscribed basically means like just inside the circle. So what the theorem states that, say you have two anchor points. In this case, let's call them B and E. These 2 anchor points, okay? And we draw, let's find another point on the circumference. So let's use this part. Let's use C instead. We have to draw, let's draw 2 lines from these 2 anchor points to that point on the circumference. So B to C and E to C. And assume that they form an angle, let's call it A. And now let's choose another point on the circumference that's not C, B, or E. So in this case, we can choose D. Now we connect B to D and then E to D. What the theorem states is that BCE, so the angle formed by C, is equal to the angle formed by D, which is BDE. The way we can prove that, we can also use Star Trek theorem again. If you notice here, so we can connect B and E to the center point, which let's call it A. So we connect those to A, and we have a Star Trek, where we have the angle A here, and the angle of BAE is equal to 2A. And similarly, we can, from D, we can also do the same thing. Remember that D, since BAE is equal to 2A, and then ABDE is also a Star Trek. It's a Star Trek with the same anchor points of B and E. So I mean, since that's 2A, then that has to equal, then angle D has to equal A as well. Are there any questions? Give me a thumbs up if you understand. KC, okay, I see a lot. That's good, right? Let's move on. So that's the inscribed angles here. Now we have the quadrilateral theorem. So this quadrilateral has to be inscribed in the circle. That means inside its vertices. Its vertices. So like it's like points right here. So B, C, D, E. they have to be touching the circumference of the circle. And what the theorem states is that the opposite angles of the quadrilateral, so B and D, those are opposite angles, and same thing for C and E, those are opposite angles. These opposite angles add up to 180. And let's try to prove that. Let's clear all drawings. Oh boy. Oh yeah, the shapes. Okay. Let's draw a circle. Let's have some here. Let's have a rhombus or something. All right. Actually, this doesn't work. Never mind. Okay. Sorry if it takes a bit long. Yeah, drawing shapes is harder than I thought with this software. So let me try my best. Okay. Oh, we have that. Now we need to draw some helping lines again. So what we can do, let's say the center. I'm just gonna eyeball the center of the circle. So let's say it's right there. We're gonna draw 4 lines. So from each of these vertices right here, of the quadrilateral to the center point of the circle. Okay, that looks good. Okay, and we'll give some names to these angles that we have made. We're gonna actually name, we're gonna have 4 different variables. Let's call one A. All right, so let's say A is this angle from this line to this line. Hopefully that's clear. Let's make an angle B. B is the angle from this line to this line. Let's have an angle C. C is the angle from this line segment to this line segment. Okay, so from here to here. And let's have D. D is the angle from this line segment to this line over here. Okay. And in fact, we can actually name some other angles as well based on these variables. And the reason why is because, well, remember these helping lines that I drew? They're all radii of the circle. Each one is a radius of the circle because they go from one point on the circumference to the center point. That's the radius. And since we know that, we have 4 isosceles triangles. So it means 2 of the line segments have to be equal, which are the radii. And that means that 2 of the angles of each triangle have to be equal as well. And so that means we have another angle A. Another angle B. Sorry, right here, that's B. Angle C. And angle D. Okay, now let's make an equation for these angles. All right, so the angles in the quadrilateral have to add up to 360 degrees. No, so any shape of 4 sides, that's a quadrilateral. The angles inside the quadrilateral have to add up to 360 degrees. So let's make an equation for that. So if A plus B plus B plus C plus C plus D equals to 360 degrees. So we can combine some of these terms. We can make that 2a, we can b plus b is 2b, and it's 2c and 2d. All right, so we have this now. 2a plus 2b plus 2c plus 2d equals 360 degrees. Hopefully that's clear. Now what can we do with this equation? We can combine, we can actually use the, factor the two from a, b, and c, and d. And we get a plus b plus c plus d. So that in brackets equals to 360 degrees. Let me write the final line right here. Now we can divide both sides by 2. So we get rid of the 2 on the left side, and 360 divided by 2, that's 180. So a plus b plus c plus d is equal to 180. So we have our theorem now. We have a plus b plus c plus d is equal to 180 degrees. Can you see why? So let's take two opposite angles, okay? Let's take this one right here, and then this narrow one right here. If you notice, this large angle is equal to a plus b. So we have that first part. Whoops. We have the first part, a plus b. That's our first angle. Let me draw brackets, just be clear. All right. And then our second angle, the narrow one on the bottom here, is c plus d. So we just add them together. And when you add those together, it's equal to 180 degrees. So that's our proof of the opposite, the inscribed quadrilateral theorem. Are there any questions? Does everyone understand? Give me a thumbs up. Oh, you guys are smart. Okay. Let's continue. Not sure how many more there are, but let's go. All right, now we have the tangent line theorem. So basically, theorem states that assume you have a point on the outside of the circle. Let's call it C. In this case, it's C. And from that point, let's draw two tangent lines. So one from C to B. So tangent lines that are that only touch one point on the circle, correct? So that means C to B. Let's draw one right there, and then the C to A. So those are your two tangent lines. And basically, what the theorem states is that the length of these tangent lines, so from A to C, let's ignore this outside part. We're gonna only look at the part from A to C and then B to C. The tangent line theorem states that AC is equal to BC. And the reason why that works is because, so we have to remember the property that a tangent line is always perpendicular to the radius of the circle. So now we have OAC, so that's 90 degrees, and OBC, that's also 90 degrees. If we notice, we can also compare some other line segments. So we have OA, that's the radius of the circle. OB is also the radius of the circle, so they're equal in length. And here we have OC, so we just connected the center point from O to the outside point, which is C. We connect that. And if you use the Pythagorean theorem, hopefully you guys remember what that is, you can take OC squared is equal to OA squared plus AC squared. And similarly here, OC squared equals OB squared plus BC squared. I'm a bit too lazy to write this out, but hopefully you guys know what that looks like. And since OA is equal to OB, and then we have, and then both of these triangles. So we're looking at these triangles right here. Since OA is equal to OB because they're the radii of the circle, and they both shared the hypotenuse, so the longest side length of the triangle, which is OC. So both these triangles share that side length. That means that AC is equal to BC. Does everyone understand that? Give me a thumbs up if you understand. I see a few thumbs up. Okay. Yeah, so just remember, so we had to draw these two triangles, right triangles actually, in fact. And we have to compare these side lengths to make sure that AC is equal to BC. So remember, we have the shortest side length, OA and OB, they're equal to each other. Both these triangles share the hypotenuse OC. And if we do Pythagorean theorem, it states that OC is equal to the radius plus the tangent, radius squared plus the tangent squared. And so now if we move, so say we have that equation, and then we move this the length of this squared to the side of the equation with the hypotenuse squared. So now we have OC squared minus OA squared, which is equal to OC squared minus OB squared. And that's equal to AC squared or BC squared. And so that means AC has to equal BC. So hopefully that's clear. Let's move on. Okay, intersecting chords theorem. So if you don't remember what a chord is, it's just a line inside the circle that touches 2 points on the circumference. And it doesn't have to be necessarily the diameter, which crosses the center. What the intersecting chords theorem states is that, so we have this point of intersection called S, and let's call the points on the outside A, B, C, D. We have AS, this line right here, times the length of CS. So these have to be the lengths of these line segments. AS multiplied by CS is equal to DS times BS. And this proof is actually a bit harder than the other ones, but I'm gonna have to introduce a new concept to you guys, unless you guys heard of it. So this concept is called similar triangles. Have any of you heard of similar triangles before? Some of you. Okay, a few of you, that's nice. Good to know. Basically, what similar triangles are is that you compare two triangles, and they're similar if they have angles that are all equal to each other. But the side lengths don't have to equal to each other, but the angles have to equal to each other. Let's see if I can, I can't draw a triangle. Okay, can't make a triangle myself. But basically, here, I'll show you later what similar triangles can do. Right, so let's say we have these two chords. Right, so let's have these two chords. Let's also draw some more helping lines. Helping lines, yeah. Let's draw a line from here to here. Draw a line from here to here. Okay, might as well name these points too, so it's easier for us to, prove it. Let's call it B. Call this D. And let's also call it S. So A, B, C, D are points on the circumference. S is the point where where these chords intersect. Right, and we're trying to prove that AS times CS is equal to BS times DS. And when we do that, we use a concept called similar triangles. So you can see here, we actually have two triangles that we just made. ABS, that's one triangle, and CDS is also another triangle. Basically, what we want to prove right now is that their angles are equal to each other. And what that means, they have to also the angles have to correspond to their specific angles, and they have to be equal to each other. So we need to compare their angles, okay? So let's call on these angles A, let's call another one B, and let's call another one C. Yeah, I don't care where these are, but yeah, let's just call them A, B, C. Okay, good. So A is this angle ABS, sorry, ASB. B is angle BAS, and C is angle ABS. Okay, so now we want to prove that these angles have to correspond to these angles over here. So if you notice here, A is actually opposite. So this angle A right here is an opposite angle for CSD. So this angle right here. So that means this angle also has to be A. Okay. And let's find some other properties. Wait, I'm trying to remember how I proved this. Okay. Okay. Sorry guys, I'm having a little bit of I'm trying to remember how I prove this chord theorem. So what I'm trying to prove right now is that the angles, so that these angles have to be equal to each other. So that means like ABS, this triangle ABS has angles ABC. I'm also trying to prove that this part over here has angles ABC as well. So let me figure out how I prove that. Yeah, sorry guys, just wait. Just trying to remember something. Oh, okay. Sorry guys, I remember now. Okay. We have to use now I remember. We have to use one of our previous theorems. If you guys remember the inscribed angle theorem, that means that say I have two anchor points, and then I have two other points on the circumference, and I draw line segments between each of those points. That means the angles that they make are equal to each other. So that's what we can use to prove this. Sorry, I kind of got a brain fart. So if we use that theorem, let's say BC are our anchor points. I want to prove that BAC is equal to BDC. That's the inscribed angles here. So that means BDC is equal to B as well. All right. Oops. All right. Okay. So we have BAC. That angle is equal to B. And because of the inscribed angles theorem, BDC must also equal to BAC, which is equal to B. All right. And then similarly, if you use the inscribed angles theorem, if you use AD as your anchor points and you draw them line segments from to B and C, you can also prove that this angle, so DCS is equal to C, or BDC is equal, sorry, B like ACD is equal to C. There we go. All right. So now that we know that they have equal angles, so we have A corresponds to A, we have this B corresponding to B, and we have the C corresponding to the C. This means that triangles ABS and triangle DCS are similar to each other. And similar means that, remember, the angles are equal, but not necessarily their side lengths. But we can also actually compare their side lengths using ratios. So the way we do that, let's take side length AS. And so this side length will have to correspond to this side length right here, DS. What I mean by correspond is that if you compare these two triangles, I mean, the ratio between these side lengths are equal to each other. So that means we have AS, so it corresponds to DS because they both have angles A and B with each other. So AB on this side, A also has AB over here. So we can compare these two side lengths, compare the ratio. AS divided by DS. Okay, and let's also do the same thing for BS and then CS. So let's do it for those side lengths. BS divided by CS. So I'm saying that the ratios of one triangle's side length divided by the other triangle's side length, they're equal to each other always. That's what similar triangles are. So now if we can rearrange this equation, let's multiply both sides by ds. So let's get rid of the ds from the left side. Let's multiply ds to here. So as is equal to bs times ds divided by cs. Okay. And now let's also multiply cs by, to both sides. So I'm going to get rid of the cs from the right side. And now from the left side, we have as times cs is equal to bs times ds. And that is our proof right there. Our proof of, it originally also said as times cs is equal to ds times bs. So we're good. So give me a thumbs up if you understand this. I know a lot of parts of it were a bit confusing, but I tried my best. Okay, sounds good. So if you guys need to know, if you guys still don't really understand similar triangles, I can explain it to you again if you want. So remember, similar triangles, we need to have angles that are equal to each other, so that and also correspond to each other. So this triangle ABS is similar to CDS because they all share angles A, B, and C. So that means they're similar, but that doesn't mean they are congruent or like their side lengths aren't equal to each other. But if we compare their side lengths, we can actually make an expression. So we can have, so we have to compare the ratio of one triangle side length divided by the other triangle side length. And those side lengths have to correspond to each other. What that means is that the side lengths, they have to have the same angles, that they have to have, the same angles on top of them. Hopefully you guys understand what that is. So I have AS divided by TS. So they both share angles A and B. So that means I can correspond them equal. I can put them in the same ratio. Similarly, we have BS and CS. They both share angles A and C. So I can put them, I can put a ratio for BS and CS. And finally, I can do AB and CD as well. They both share angles B and C. So AB divided by CD. And the order of these ratios, so like where the denominator is and the numerator is, the order matters. So like if you have a side length, if you have one triangle's side lengths on the numerator, they all have to stay on the numerator. Otherwise, this comparison of ratios doesn't work. So AS, BS, and AB all have to be in the numerator, and DS, CS, and CD, those are side lengths from the other triangle. They have to stay in the denominator. Is that clear? Give me a thumbs up if you understand. Okay. And if you're still a bit confused about similar triangles, you can just search it up. Shouldn't be too hard to understand. All right, last one, the alternate segment theorem. What this states is that, say we have a triangle inside the circle. In this case, it's PXT. And say we also have a tangent line that crosses one that is tangent or crosses at one of these points on the circumference. So let's call that point T. We draw a tangent line that crosses at T. So right here. And say this tangent line has endpoints T1 and T2. What this theorem states is that the angle P to PTT1, so this green angle highlighted right here, is equal to angle PXT. So this green angle right here. So basically the angle that is made between a tangent line and one of the side lengths of the triangle is equal to the opposite angle inside the triangle. So if you can, so basically this angle is made of PT and T to T1, right? And this angle will be equal to the angle of PXT. So basically looking at like opposite ends, if you understand what I mean. Let's actually try to prove this. All right. Draw a circle. Okay. There you go. We have a triangle. All right, and finally, let's get our tangent line. Yeah, right here. Wait. Okay. Tangent line. Never mind. Sorry. It's going to take a little while. Just draw it right there. Okay. So here's our tangent line, and here's our inscribed triangle, which is inside the circle. Now what we're trying to prove, this angle right here is equal to this angle. Let's give names to our points. So A, B, C, D. Okay. So now we're trying to prove DCB is equal to BAC. And just like the other theorems we use, we're going to draw some helping lines to help us out. Let's draw a line from each of ABC to the center of the circle. Let's call that center O. All right, so I'm just eyeballing the center right here. So A to O, B to O, and then C to O. All right, there you go. All right, now let's give names to these angles, as we have done before. Okay, let's also name this point, right? O. Just put it right there. Angle O. All right. So let's give names to these angles. Let's call that lowercase a. Sorry. So OAC, let's call it lowercase a. Let's call OBA. So this angle right here, let's call it B. Lowercase b. And let's have a lowercase c. Let's call OCB right here. So this to that. Angle C. All right. And if you notice, we also end up with some 3 isosceles triangles. So remember, AO, BO, and CO are radii of the circle. So that means for each of these triangles, we have 2 equal line segments. And that means we have 2 equal angles as well. So that means this angle here is also equal to A. This angle here is equal to B. And this angle here is equal to C. All right. And finally, let's try to get an equation that for these angles. So if you remember, angles in a triangle have to add to 180 degrees. So let's make an expression for that. So if A plus A, here let's write that as 2A. Hopefully you guys understand why it's 2A. And we also have 2B's, so it's 2B plus 2C. So those are all the angles inside the triangle. So A and A, B and B, C and C. And they all add up to 180 degrees. So we have AB, that's one angle of this large triangle. B plus C, that's also another angle of this large triangle. And A plus C, which is also an angle of this large triangle. And you add them up, you get 2A plus 2B plus 2C is equal to 180 degrees. Okay. And similarly, we can also factor out the 2 from the 2A, 2B, 2C. But I'm just going to skip that step. And I'm just going to write A plus B plus C. Oops. C is equal to 90 degrees. So I divided both sides by 2. So I got rid of the 2 from 2A, 2B, and 2C to get A plus B plus C. I divided 180 by 2 to get 90 degrees. Okay, so now how does this expression help us? Let's use another property of circles that I've mentioned before. If you remember, the tangent line is always perpendicular to the radius of the circle at the point where they intersect. So that means the angle that is made with OC and CD is 90 degrees. So let's draw that in. Right here. Oh, never mind. Let's just draw 2 lines. So I'm going to draw this. Right. So remember, OCD is equal to 90 degrees. Hopefully that's clear. Okay. So now we have this. We also have this angle C, which is part of that right angle we see right here. So this angle is OCD, but angle C is OCB. So now we can compare those angles. So remember, we have OCD is equal to, if we actually compare angles, we can see that OCD is equal to OCB plus BCD. So we're just adding up those angles. OCD is equal to 90 degrees. And we have OCB, that's angle C right here. And we have BCD. All right, so that means BCD is equal to 90, subtract C. Okay, so this is what BCD is equal to. And remember, we also have this expression, A plus B plus C is equal to 90 degrees. Actually, I shouldn't have done that. Let's just keep this line and see how these two compare. So we have 90 on one side, then we have C. We also have a C on the other side. So that means BCD has to equal A plus B, because we have these two equations right here. And if we compare them, we have BCD is equal to A plus B right here. So that means A plus B plus C is equal to 90 degrees. And we have proved the theorem. So if you look over here, so this is BCD, okay? And we're trying to prove that BCD is equal to BAC. And if you see BAC is equal to A plus B. So we have proved the theorem. Give me a thumbs up if you understand. This is also a long proof, but hopefully you understand. Okay, we are running out of time to do some questions, but let's try to do some problems that use these theorems. So hopefully you guys understand how we prove those theorems. I know it took a little while, but I want to make sure that you guys understand where they came from, not just like, I'll just give you this information, just use it. You need to understand like how to prove these, so you get a solid foundation of mathematics. Okay. All right, let's have this problem. What's the value of angle ABD? So this angle right here. I'll give you guys a moment to solve that. Yeah, just give me a notification if you have the answer, and I'll unmute you. Or you can type your answer in the chat. Does anyone have an answer for this? Okay, so we have a chat. 63. Nope, it's not 63. Close. Oh, 67. Yeah, 67. Okay. So the answer is 67. So good job to Kevin, who got that answer. And why is it 67? So let's look. Oops, sorry, okay. So we had the circle, and we also had a diameter. So remember, across the center. All right. We have a circle, and we have this diameter. And we also have a triangle. Whoops. Sorry about that. We also had a triangle that crosses both these points on the diameter and to another point on the circumference. Here you can use the right angle proof, the right angle theorem. So that means that the angle made by this triangle right here, this angle right here is 90 degrees. Oops. So this angle right here is 9 degrees. So that's our right angle theorem. And one of the angles was 23 degrees. So I'm just going to write that down. 23 degrees. And remember that angles in triangle add up to 180. So let's just make an expression for that. No, 23 goes on the other end, but who cares? So we're trying to solve for this angle. So we're going to write an expression for that. 180 is equal to 23 plus 90 from the right angles here, plus what was our angle named? Our angle was called ABD. So it's called ABD. And if you solve this equation, you get ABD is equal to 67 degrees. All right. Are there any questions? Give me a thumbs up if you understand. Okay, sounds good. Guys, don't be afraid to ask me questions. I know this is a really tough tough topic to learn. So just hit me up with questions if you can, and I'll be glad to answer them. I want you guys to make sure you actually understand these concepts. Okay. Here, ABCD is a cyclic quadrilateral. So that's another term for a quadrilateral that's inside a circle. So we have O as the center of the circle, and we have angle ADC is equal to 160 degrees. Sorry, 116 degrees. And we're trying to find the value of angle AOC. I'll give you guys a moment to solve that. So you're gonna have to use actually two theorems. You have to use the quadrilateral theorem, where opposite angles add up to 180. And if you notice, we also have a Star Trek. We have ABCO. That makes a Star Trek. So we can use the Star Trek theorem. So does anyone have an answer? $64. Here, let me see. No, you got part of it. It's not 64. It's way bigger than that. It's close. It's got to multiply. Yeah, 128. Yeah. No, it's 128. So here, I won't pick up the whiteboard. I'll just do it on the slide. Okay. So we have ADC is equal to 116 degrees. Remember that ABCD is a quadrilateral, inscribed quadrilateral inside the circle. And if we use the quadrilateral theorem, we know that ADC plus ABC is equal to 180 degrees. Okay. And so if we solve for ABC, that makes it equal to 64 degrees. So 116 plus 64, that should equal 180 degrees, right? So now we have ABC is equal to 64 degrees. Now we're trying to solve for AOC. And here we can use the Star Trek theorem. So that means AOC is 2 times ABC. And 2 times 64, that gives us 128. So AOC is equal to 128 degrees. Are there any questions? Give me a thumbs up if you understand. Okay. Okay, see a few thumbs up. Okay, it sounds good. Okay, we have, let's see, 1, 2, 3, 4 more problems. Okay, so we have 4 extra problems that we didn't cover today. Do you guys want to do one more, or do you want me to end it right now? Give me a thumbs up if you want to do one more. So let's just solve this one. Okay, see a few. It's only 2 of you. I want a thumbs up. Okay. Okay, let's just do it. Let's go just a little bit over time. We'll just end it with this problem. Okay, so here we have AB and BC are tangents to the circle with center O. Point D right here is a point on the circumference, and it's outside this range, this area right here. The angle of ABC is 65 degrees. What is the angle of ADC? So you're gonna have to use a few theorems again. So remember, you have tangent lines. Here you have a Star Trek. ADCO is a Star Trek, or whatever you want to call it shape. It's a quadrilateral in mathematical terms. So I'll give you a hint. The first theorem you're gonna have to use, remember that. So AO and OC, they are each radius of the circle. And if you remember from our the property of tangent lines to a circle, so tangent lines are always perpendicular to the radius. So perpendicular as in 9 degrees. So that means you have some 9-degree angles, which you use to help solve your problem. And finally, you can use the Star Trek theorem with ADCO to find ADC. Does anyone have an answer? So here, we want to find AOC. And we have a quadrilateral right here, ABCO. That's a quadrilateral. And the angles inside the quadrilateral add up to 360 degrees. So that should help you. Can't be a decimal number. 57.5 can't be possible. Remember, we're just adding angles, adding and subtracting angles. Actually, wait. Sorry, it could be. Wait, let me see. It's possible. 57.5. 15. Yeah, sorry. Okay, it is 57.5. Sorry about that. Yeah, 57.5 is possible because we're dividing by 2. I forgot about that. So basically how we find the answer, we have, remember, ABCO is a quadrilateral. And so that means its interior angles have add up to 360 degrees. So here we have 65 degrees. But then we can also use the tangent line property that tangent lines are perpendicular to the radius. So BC and AB are perpendicular to OC and OA. So we have some 90-degree angles right here. So BAO is 9 degrees, and BCO is 9 degrees. And now we have 3 angles, and we're trying to solve for 1 angle. So, and we can solve for it, right? We can take 360 and subtract the value of each of those angles. So 360 subtract the 2 9 degrees. So it gives us 180 degrees. And now 180 subtract 65. That should be 115 degrees. So AOC is 115 degrees. Is that clear? Hopefully that should be clear. Okay. And then since that's 115 degrees, that's part of the Star Trek of ADCO. So now we can use the Star Trek theorem so we can divide AOC by 2 to get ADC. And so 115 divided by 2, sorry if it's a decimal, but it's 57.5 degrees. So give me a thumbs up if you understand. Okay. Let's see if you, okay. I'm just gonna end it here. Don't want to waste more of your time, but I will share the slideshow with you later today, and also the homework questions and the answers. So now we're gonna end the meeting. Okay.
Bye.
Yep. You guys can unmute yourselves now. Thank you so much. Yep. Hopefully you guys were able to understand these concepts. I know it's a tough concepts, but yeah. Right. I will end the meeting now. All right, everyone. Goodbye. Stay safe, and I'll see you next week.